Yeah. Okay, Freddie, you're up. How about the x and y quantities here?
X is each like a time.
Okay, what? So the time is that we know that's not. What's that?
Hour that passes.
Okay, but so we want a good, well-defined variable. So hours is the unit. That's true. So what amount of time is it?
1 hour.
As a description of the quantity. Yeah, Faisal.
The amount of time it takes for the cell to split into 4 cells for each hour.
Okay, the amount of time it takes to split, that's 1 hour. So, but this quantity can take on 0, 1, 2, 3 hours, 20 hours. It could take on all this, not just 1 hour. So,
The amount it takes.
what's that?
The amount of time.
Amount of times, and we always need, for time and distance, we always need that reference starting point. Time since, what?
The cells began dividing.
Yeah, you can say the time since the cells began dividing. The time in hours since there were 7, right? Or since I think I wrote since the first observation. Any of those. Hours since the first observation. Okay? What about y? So a well-defined variable for y, or quantity well-defined. Let's see. Aaron, did you get that? What did you say for the defining the variable y? John, what do you think?
Number of cells.
Yeah, number of cells, right? So that's what we're interested in here. How many cells in the number of cells present, or number of cells in the sample. Okay? All right, so at 0, so number 2 is to use product notation. At 0 hours, what is our number of cells? 7. Easy. All right, remember we're going to use product notation now. So how would you use product notation to describe how many cells after 1 hour? Janessa?
7 times 4.
7 times 4. Okay, after 2 hours, who had their hand up? Zach?
7 times 4 times 4.
Right. Okay, 3 hours. Too easy now. Right, don't have to think. All right, how would we do it for 20? So how would we do it for 20? So how could you describe it in words? The number of cells after 20 hours would be, describe it in words. Sean?
In words?
Yeah, so how would you get the number of cells at 20 hours?
Do you still want me to try to do the product thing, or sorry?
Just describe how you would calculate that, yeah.
Well, it would be 7 times 4 for the amount of hours, so 7 times 4, 20 times.
Exactly. 7 times 4, 20 times. So we can do it that way. You can use ellipses like this. Ellipses means keep going like this, but then we should kind of specify that we're talking about, what are we talking about? 20 fours. Okay? And then what about after t hours? Jay, did you get that? How would you describe after t hours how you would calculate how many cells in a sample? Can you just describe it? Describe the computation you would do. 70. Michael, what do you think?
If you're writing the product notation, you'd do the same as the example for 20, only with a t in place of it.
Well, so tell me how you would calculate it instead of just saying this is how I would change that one. So how would you calculate it?
7 times 4, t times.
Right. So we're going to take 7 and multiply it by 4. T times, right? T force. Okay, 7 times 4 T4s. Okay, so how is the sample growing? So specifically, mathematically, how is the sample growing? Awesome.
It starts at 7, and then each hour it splits. Or each of the 7 cells splits into 4 new cells.
Okay, so now summarize that mathematically. What's happening? So that's just kind of like the way it was described. But mathematically, how is the number of cells growing? So that's by looking. So we're looking at what is happening every hour.
7 times 4 to the power of 2.
Okay, but that's not my question. My question is, how is the sample growing? How is that quantity increasing? What's that? It quadruples every hour, which mathematically is what? Yeah, every hour the sample gets multiplied by 4. And so then, if we wanted to write this in exponential notation here, after 20 hours, it would be 7 times 4. No, after 20 hours. To the 20th. And when you see 4 to the 20th, immediately you think what? What does that mean? Yeah.
Multiply 7 by 4 times. By 4 20 times.
So 4 20s or 24s?
24.
24. So you're multiplying 7 by 4 20 times, right? 24s multiplied by 7. That's what you have to think. Remember what we talked about. When you see a graph, what is your image of it? What do you think immediately when you see a graph? Or you should. Does anybody remember?
Infinite number.
Points. You're looking at points. You're looking at a zillion points. That's what you're really looking at. When you're looking at 4 to the 20th, what are you really looking at? 24s multiplied together. You're looking at, you see that, you go, oh, that's 7 times 4 times 4 times 4 times 4 times 4, 24s, right? That's what you think when you see that, okay? And so what about when you multiply T4s together? What you doing there? Is that math? Really? So what would we do? Ready?
Times 4 to the T.
And what does that mean, 4 to the T?
That as many hours passes, it will be T, and T will be multiplied by 4 x. I don't know how to explain it, but I get it.
Right, because you're on your smartphone. What does 4 to the T
I don't know how
mean?
to explain it.
Dan, what does 4 to the T mean?
4 to the T means that 4 is exponentified to the T power, which means it's multiplied by 4 T times.
It's multiplied by 4 T times. Agree with that? It's multiplied by 4 T times. That's right. You're multiplying by 4 T times. Okay? So then how we could write our function? What are we doing? Cells. So cells, C of T equals. So if this is the number of cells, that's our output after T hours. We know what we do. We start with 7, and then we start multiplying by 4. How many times do we multiply by 4? T times, and so that is. So what is the key operation at work? Addition, subtraction, multiplication, division, or exponent? What's the key operation at work? The key operation at work is multiplication. The exponent is just shorthand. It's just a way to represent multiplication. This is all about multiplication by 4. Okay? And we're multiplying what by 4 to get what? We're multiplying what by 4 to get what? So, tell the person next to you. You're multiplying, in this growth, we're multiplying what by 4 to get what? Ready? Give it to me. I'm taking a smartphone. That'll be an example. Okay, this function represents multiplying what by 4 to get what? Anybody say no? How about, I think Dan knows, how about Maddie? Multiplying represents?
The function represents multiplying the number of cells by 4 to get like final number of cells.
Okay, so it represents multiplying a number of cells by 4 to get Which- the final? Is there a final number of cells?
No.
So you got the right idea. So it's multiplying the number of cells, or multiplying, is that input or output? Number of output, multiplying the output by 4 to get? What do you get when you multiply the output by 4? The new input. You get the new input. The next output. You get the next output. The next number of cells. Or the number of cells 1 hour later. Okay? This is what exponential growth is about. It's multiplication by the growth factor. In this case, the growth factor is 4. The growth factor multiplies on output to get the next output. It multiplies on output to get the next output. That's what exponential growth is about. Okay, so let's summarize that here. I think down here I have that. Exponential functions are about repeated multiplication by the same value over and over again. And what is that value called? The growth factor. And it's that the growth factor is the multiplier on output to give the next output. This is the key to it. So as you're in this whole module for the next 3 or whatever weeks, every problem that you come to, this has to be your kind of your baseline understanding of what's going on, or you're always thinking in the context of this. That there's some number, and to get the next output, you're going to multiply by that number, and that number is going to stay the same. That's exponential growth. Yeah?
Terminology question.
Yeah.
In coding, something like this would generally be called like a recursive function. Is that the same thing? Where you basically just keep putting the function into itself, right?
Yeah, so what you're saying, good. So you're saying that the next, so if the current output is f of x, what's the next output? How would we represent the next output? Right, it's on the screen. What is it?
F of x.
No, that's not the next output.
Oh, just output? Well,
So if f of x is the current output, then how would we represent the next output? This is a great question. Everyone try to think about what that is. What am I doing? What's going on? Oh, this thing again. Yeah, it always does that. So if f of x is the current output, how would you represent the next output? So look, so here's your current output, and say that's f of x. How would you represent that? That's what we're saying. I think everyone should think about this. Let's talk with your neighbor. This is a great little question here. If f of x is the current output, how would you represent what we're calling the next output? Agree with the person next to you. See if you can come up with it. Okay, Jenna's going to tell me. What do you think, Jenna? F of x?
Yeah.
No, we're not taking a number of bacteria and plugging it into the function, right? Only time gets plugged into the function. So if the current output is f of x, say this one's f of 2, right? What's the next output? It is 4 times f of 2, but how can we represent it? F of 3. So if f of x is the current output, what's the next output? F of x plus 1. That's what you should... How many people got that before we said it? The next output is referring to advancing the input by 1. Advancing the input by 1. And what's the next output? Right? So how do we advance the input by 1? We add 1. So what Michael was saying is that you get the next output by multiplying the previous output times the growth factor. So this is yes, this is a recursive idea. So you could express it recursively. That the next output is the previous output, or the current output, times the growth factor. That defines that function. Is that what you were thinking, Michael?
It answered the question, not quite what I was thinking. I was thinking more about f of x scenario.
F, so think about this, guys. F of, and a lot of people are saying this, so that's why I want to talk about it. What is f of x? What is f of x? What quantity is it?
7 times 4.
No, what quantity is it? Number of cells. So we're taking the number of cells, and we're going to put it into f. What's the input into f?
Time and hours.
Time and hours. Doesn't make sense. You're trying to put a number of cells back into the function f that wants number of hours. It says, no, delete, error message, right? This doesn't work. This is not my function, is to take a number of hours and give you a number of cells. Now you're trying to give me a number of cells. That's what f of x is doing. That doesn't make sense. It doesn't make sense. Dang.
I don't know if this is valid or not. Like, is it possible to get something that's like, if we're going to define number of cells as a g function, but like, is it possible to be like g of f of 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 x? Or is that? There's just not one.
Well, so what is the function g?
G would be the number of cells. The function g would be the number of cells.
What's the function f?
Yeah, or just this first calculation.
No, a function is two quantities, input and output, right?
Never mind that.
Yeah, so that's not right. Okay, does this make sense? Okay, cool. So now I want you to go to the next section in the, I think, let's see. Look at Module 4, Section 2. It should be about North and South High School. North and South High School. What is it? Page 131.
Is that 2 schools or 1 school?
2 different schools. Why? 2 different schools. Yeah, that would be weird. I agree. Let's see if your results came up. There they are.
Oh boy.
What? No, I'm just gonna. I'll do this while you guys are working on something. All right. Okay. Let's see. So I want you to start doing this. Let me see what we're looking at. Module 4, Section 2. All right, so everyone listen. I'm going to change the setup. You got to listen, because every semester we get all the way in this, and then some student didn't catch this change, and I roll my eyes. Everyone listen. We're going to change the setup. It says the current enrollment of South is expected to decrease by 3% per year. Change that to increase. South High School's enrollment is increasing 3% per year. Do I have everyone? Did everyone get that? Because you don't want to do a bunch of work the way it's written, and then we're all doing something different than you. So, South High School's enrollment is increasing 3% per year. North High School is increasing. They both increase by 20 students per year. Both of them increase. Both enrollments are going up. Both enrollments are going up. Did it make it into all ears? Did it make it into all brains? Okay. So, I just want you to make the table. I want you to work on the table. Just maybe the first 5 rows. You don't have to do the whole table. Did they? No, both. So did they give you the projected starting enrollments here? I think South, they say, is in 1980. Is that right? Thank you. Everything's the same as what's written. It's just they both increase instead of decrease. So South is increasing by 3% per year. And North starts at 1760 and increases by 20 students per year. Okay, so you're going to find, just do like the first 5 years, or even just 4. First 4 years for both schools, delta T, output quantity, delta S, delta T, output quantity N, delta N. Please.
When dealing with people and doing the percent, obviously will eventually get decimal somewhere.
Yes.
Point when you're doing that, do you round it down to the next person? Does it really?
Yeah, round it to the nearest whole person.
So like,
yeah, so round up if it's greater than 5, round down if it's less than
if
5.
you're doing a more complex thing, it's like using the percent afterwards or something. When would you round in that scenario? Do you round at the end? If there was like more to it, obviously.
Case by case basis. I've had to see, you know, like, you have to make that decision based on what you're doing. There's not really no hard and fast rule. All right, compare your numbers with the people around you as you're working, so you don't dig in. But you only need to go to 4 years or so. Let's fill out the whole table, all the columns.
Just 5 years, right?
What?
Just 5 years.
But every column. Do every column. All whatever, 4 or 5 columns. Did I ever?
These good results.
Typical. Never good. That's per item. These are by items. Here are the class results. Raw.
Oh.
So 4 in the 80s, 4 in the 70s, 8 in the 60s, 17 below 60. What's that? No, I have to do all that. This is just a PDF document that I get. Okay, how do we do? So let's start with north. What is delta t over here from 0 to 1 year? What's delta t? 1. What's delta t here? 1. So this is the idea of the next input. By just going up by 1 each time, this is what we're talking about, the next input giving the next output, okay? What is delta n from year 0 to 1? Plus 20. Not minus. What about delta n? So then, therefore, what is the new enrollment after 1 year? So easy, right? And then 20, 1800. Is this what you did? I hope we all got this. We'll do one more. That's what I told you to do, up to 4 years. You're adding 20 students every year. So that's how the enrollment is going up. Okay, now how about this? Make myself some room down here. Okay, that's good, I think. Okay, so I need a little room to write down there. So let's talk about how we did this. So what about delta t? Delta t for plus 1? What about the next year? Again, input increasing by 1 is what we mean by, quote unquote, the next input, which would give us the next output. Okay, so increasing 1 by 1. So now we want a 3% increase. So we need to get 3% of 1980. Did you find 3% of 1980? Some of you? How'd you do that? Dan, how'd you get 3% of 1980?
I multiplied 1980 by 0.03.
Okay, 1980 by 0.03. And when you do that, what do you get?
You get 3% of 1980.
Doesn't have a calculator. That's true. That's a true statement. What is it? 59.4. So I told you to round to the nearest 59. So what does that tell us right away in terms of our table? So 59. So the enrollment after 1 year is 59. No, what is 59? Delta t, right? That's how much it went up. This is plus 59. Okay? So how do we get the enrollment then? You add it to 1980. So you're going to take 3% of 1980 and add it to 1980 to get the new enrollment. And what is that? 2039. Okay? And so then, how are we going to get the enrollment the next year after that? So now I've got 2039. Okay? Yep, that's what we're going to do. So get 3% of it and add it to what you started with, right? You're going to take 3% or multiply by 0.03 and then add what you had before, the 2039. What is 3% of 2039?
61.
He said 61. Is that right?
Yeah,
61. And then we get 2100. Okay? So, looking at the delta t's, what's the difference here? What's happening in North High School? Looking at the delta t's here. Same number of people are coming every year. So what operation is that? What operation? Addition, right? This is additive growth. Additive. So what? Every time, listen to this. This should sound familiar. Every time you change the input by 1, you change the output by 20. What is that? Constant rate of change. That was one of our 3 mathematical results of constant rate of change. Equal changes in input result in consistent change in output. That's exactly what's happening here. Every time you increase the input by 1, you increase the output by 20. Every time you increase the input by 3, you increase the output by 60. Right? This is constant rate of change. So we can think of constant rate of change as additive growth. So we didn't really say that before, but this idea that you always change by the same amount means additive growth. Do we have additive growth at South High School? No, because this is what's happening to that number of new enrollees. Increasing. What's the next? What isn't it? Plus 59, plus 61, then what? 63, 65, 67. And at some point here, that jump is going to be bigger than 2 also, right? So at some point, it's not going to always get bigger by 2, right? But the main point is that increase is getting larger. So we got 2163, 22, 28, thank you. And then one more. Thank you. So is that constant rate of change? Equal changes in input are resulting in equal consistent changes in output? No, it's not consistent, right? It's first it's 59, then it's 61, then it's 63. The amount of change is increasing. So this is not additive growth. But let's take a look at something here. So this right here, this 1980, or let's just do the second one. Or any one of them, right? Any one of the outputs, you could go through that process of what? Multiplying by 0.03 and then adding what you had. So let's just take the 2100. So 2100, to get the next output, you take 3% of it, and then what? This is key. You add 2100 to get the next output, is that right? So watch this. I'm going to factor out 2100. And what will I have when I factor it out 2100? 0.03 plus 1. And that is 2100 times 1.03. So this process of taking a percent, don't miss this, taking a percent of something and then adding it to what you started with is the same as doing what? What operation? Is it addition? To get the next output? So this is getting us the next output, right? 2100 times 1.03 is getting us the next output. And what's the key operation? Multiply, times. So what kind of growth is this? This would be true for any one we picked. If I picked 2228 here, it'd be times 0.03 plus 2228. 2228 times 0.03 plus 1. 2228 times 1.03. So every single output, we could multiply by 1.03 to get the next output. What do we got? This is exactly what we said exponential growth was, right? Growth by multiplication on the output, right? So this is where the other one, North High School, is additive growth. This one is multiplicative growth. And multiplicative growth is what kind of growth? Exponential. So additive growth is constant rate of change. You keep adding the same value to your output to get the next output. That's constant rate of change. Multiplicative growth, you keep multiplying the old output to get the next output. We know that that is exponential growth. So, South's enrollment is growing exponentially. True or false? South's enrollment is growing exponentially. Attendance says true. It's not very getting much bigger very fast, though. Isn't it supposed to? If it's growing exponentially, isn't it like, you know, 1 year it's 2,000, the next year it's 5,000, the next year it's 20,000? No, that's just the way people in the world use the term exponential growth. Exponential growth is any kind of multiplicative growth. So even 3% growth, a very slow growth, is exponential growth. Okay? Okay, so can you write the function for North's enrollment and for South's enrollment? So we'll call, for South's enrollment, we'll call it S of T, and then North's enrollment N of T, after T years. So capital S of T equals what? I'm running out of room here. Capital N of T equals what? So what does each function look like? Who can do it? What do we think? Let's see. Jenna, how about somebody new? Let's see, someone who hasn't talked today yet. Abdullah, you get your pick. Do you want to do S of T or N of T?
S.
You want to do S of T? What do you think it is?
1980 multiplied by 1.03.
1980 times, multiplied by?
1.03.
Like that? Is that the function? That's just, well, you just get a number there. If you do that, you just get, that'll just be the, what? The output for 1, right? So that would just be 2039. But I want to know what the population is any T years after that starting date. Who else have I not talked to yet? Yeah, Cecilia.
Could it be 1.03 t plus t?
103t plus t.
From S.
So let's do this. Instead of this delta, so this delta S column is really kind of useless for us, right? Because it's tracking how much we add. Really what we are interested in here when it comes to the output is what's happening to the output? Increasing how? How do we get the next output? Every time. Okay, but then we said that's the same as what? Times 1 point multiplicative growth. So rather than what we add each time, it makes more sense on this one to talk about what we multiply by each time because it stays the same. We said it's exponential growth, right? So we have that initial enrollment. In 10 years, can you describe how you would calculate the enrollment in 10 years? So every year we're multiplying by 1.03. So if we start at 1980, after 10 years, how would you explain how you would calculate an enrollment? Yeah, Zach?
Should I like tell you like what I got?
No, I want you to explain it to me. How does the year after the number of students after 10 years, how would that be calculated?
You could take 1.03 to the t power to figure out and plug t is 10.
Yeah, so that's exactly. So I'm not picking on you. That's exactly not what I want you to say. not what I want you to say, but not how I want you to think about it. Okay. So when you do that, what you just said, what is happening? That's what I want to know. What is happening? So how would we think about what the enrollment is after 10 years? How would we think about what the enrollment is after 10 years? Valerie, any idea? How is it growing every year? How is the enrollment growing every year?
Oh, yeah.
Yes.
Growing 3% every year.
Okay, but then what does that result? How do we get the next? How do we increase by 3%?
You multiply by 1.03.
You multiply 1.03. So in 10 years' time, what would the process look like to find the enrollment after 10 years' time? So Valerie, what would that look like after 10 years to get that enrollment? Jonathan? 1.03 multiplied 10 times, and then times what? Right, you would start with 1980, and then for every year you multiply by 1.03, so after 10 years you will have multiplied it by 1.03 10 times. So after t years, and that's what I heard you say. That's right. So after t years, it's going to be that starting value of 1980 times 1.03, what? Not raised to the t. That's just a shorthand. I'm trying to get you to understand, what does exponent mean? What does an exponent mean? Or what should you think when you see an exponent? So you're going to take that 1980, and then in 10 years' time, how will you have a new enrollment? Multiply by 1.03 10 times. Every year, you're multiplying by 1.03. So after 10 years, you will have multiplied by 1.03 10 times. So what about t years? You're going to multiply by 1.03 t times. And so now, to write that, we use an exponent. Exponent is just a way to make it easy to write, but it means multiplication. So 1980 times 1.03 to the t. And that 1.03 to the t, you see that and you think, oh, 1.03 times 1.03 times 1.03 for every year that goes by. T years. Okay, what about n of t? Anyone want to take a shot at n of t? What's that? It's a lot simpler? Well, can you tell me what it is?
So t equals
Okay, I know Jake knows. Allah.
I think it's 1760 plus 20 raised to the 20
1760
plus 20 and multiply t times this one.
So 20
Raised to t.
raised to the t.
Oh, actually, it's 20 t.
Good. He thought it through. Here it's additive growth, right? So 760 plus, what does 20t mean? What do you see when what do you think when you see 20 times t? 20 plus 20 plus 20 plus 20 t times. So multiplication models addition and models adding the number together that many times. We're adding, right? Exponential or exponent means multiplied by that many times. So that's consistent with, we said, south is multiplicative growth, north is additive growth. So this multiplication right here, it means add together 20, t times. 1.03 to the t means multiply together, t times. Okay, what's next? All right, let's try this. What's this? Yes. Okay. This is page 3, I believe. Nope. Okay, number 9 on page 165. Does it say that there's some mass and it's decreasing by 12% every hour? Go the same? Good. All right, so I just want to use that particular, is there a table or something about it here? So just we're just going to use that setup, and now I want you to work out this table. Okay? If it's a 12% decrease of mass each hour, then how would you, so I'm going to say X is the number of hours after applying a chemical, Y is the mass in micrograms starting at 203. Okay? So now I want you to work on this table. Finish making this table from this situation. This is a decrease of 12%. Okay. Yeah, so that's where we're going. They taught you to subtract. Yeah, my thinking here, so my idea here was that she would figure that out. How you would get 12.
Yes, yeah.
Okay, so Sarah, did you start by finding 12% of 203? Did you do that first?
Yeah.
Awesome. That's what I wanted to do. So how did you get 12% of 203? Okay, so Sarah, so we're gonna regroup here. So Sarah started by taking 12% of 203, and so that's 0.12 times 203. And then once you got that number, then how did you find the number of the mass 1 hour later? Okay, so you took all of that, and you took 203 minus all of that. Is that right? So now instead of adding the percent of the original, now we subtract that percent of the original. And you said that was? 171? 179. Now we can have decimals because it's mass, right? Mass is continuous quantity. So can we do 10th to the nearest 10th? 179 point... 78.64. So now look, we can do the exact same thing we did before. We can rearrange this by factoring out 203. 203 times what? Okay, one step at a time. I factor out 203, I get. This middle step is important because it's what we're going to use here. 1 minus 0.12. Which is? So decreasing an amount by 12%, you can do that mathematically by multiplying by 0.88. So doing this process, 203 minus 12% of 203 is exactly the same as just taking 203 times 0.88. You get the same thing. Okay? And that's more convenient, right? So to get from there to there, we're going to multiply by 0.88. Okay? And that's 178.64. Okay, so I'm going to use my spreadsheet to do that. Watch. So I'm going to say this cell equals the cell above, right, times what? 0.88. But it's got to be turned on. So I'll clear the contents here. Contents. And then I'll make it black. Okay. And so then I can say this equals what? the previous output, B5, times 0.88 again. So that's really going to be the pattern. So all I have to do then is grab onto this cell and copy it. And it keeps giving me, it's always taking 0.88 of the previous output. And that we know what kind of growth is that? Exponential. But now this is not growth. Decay. Exponential decay, because it's a decreasing quantity. But it's still exponential, which means we multiply by, now it's a decay factor, times 0.88 every time. So a decay factor is just like a growth factor. It's the multiplier on what to get what? Multiplier on what to get what? He wants the output to get the next output. Agree with that?
Yep.
It's still a multiplier on output to get the next output. Now what does the decay factor mean? That 0.88. What's the meaning of that value, 0.88? Is there anyone I have not told them? How about, yeah. I love your enthusiasm, your participation. I want to get everyone involved. Nathan, what is the 0.88 about? How would you describe what that number is? 0.88 is what?
It is the rate at which the bacteria is decaying.
The rate at which, not quite. So it's not really a rate. What is the 0.88, Jacqueline? What's that number about? A big finale here. Really important. 0.88 what? Is that? Fajita, what do you think? 0.88. It's the decay factor, but that number 0.88 signifies, symbolizes, or represents what? Is it the amount of decay? The percent of decay? No, what is it instead? What would 88% be? Yeah, 88% is what? The what? Remaining is what gets kept, what you keep. So here's the thing about decay factor. You have to see that. What that is this is the portion that you keep. What was the amount that we lost? 12%. So we're keeping 88%. So the decay factor is the portion that you keep, or the portion that remains. The percent that it remains, 88%. All right, what is the function? I still got a minute or 3. What's the function? So if we want to do b of x. So we start with 203, and then x hours later, how do we calculate it? Zach, let's go for it.
203 times 0.8 to the x power.
And why is it that?
Why?
Hmm?
Because for every hour that goes by, your decay is 12%. So if you multiply the 203 times 0.8 to the x power, you can take how many hours you have and multiply it times the decay factor and multiply it with the original amount.
Okay. Dan, what were you going to say?
I was going to say the exact same thing.
You're multiplying, so if x hours go by, how many times did you multiply 200 by 0.88? X times. If x hours go by, you take the 200, you multiply by 0.88 x times to get the final amount after x hours. So that's our function. So remember, decay factors, those will be less than 1 because it's going down, but that's the amount you keep. That's the amount you keep, not the amount that you're losing, right? You know that the amount we lost was 12%. We're keeping 88%, and that's what your decay factor is. Okay, I'll have homework up in the next hour or 2. Have a good weekend.